Welcome to the 1961 Nobel Prize in Physics. This prize, a lot of times you'll see a prize shared between multiple individuals that worked on the same project. This year it was a divided prize, which is a little bit different. It's two people who contributed to the same area, but in completely different ways. They came at it from different approaches, usually in different labs, and in this particular case, it was different countries. This one went to Robert Hofstadter. If you've seen The Big Bang Theory, no relation to Leonard, but there is a theory running around that the Leonard's last name was in honor of Robert Hofstadter, and Rudolf Mossbauer. So Hofstadter won for his work in electron scattering, which allowed you to learn more about nucleons. Nucleons is a big physics or chemistry way of saying stuff that makes up the nucleus. In other words, protons and neutrons. So when you hear nucleons, think protons and neutrons, or nucleus of the atom, the stuff inside the nucleus, which we now know to include things like quarks, but quarks are inside proton and neutrons. So, anyway. Rudolf Mossbauer won for his research into resonance absorption of gamma radiation, which led to the discovery of a thing called the Mossbauer effect, which led to Mossbauer spectroscopy. And what these two guys jointly did together was they gave tools and techniques that allowed scientists to gain a more full understanding of the nucleus and what's in it and how it's built and how it is held together and what resonance effects there are, all kinds of cool stuff. So with that in mind, let's dig in and see how this stuff works. This one's going to get a little more technical than most because this is getting down and dirty in the nucleus. So, we want to look a little more carefully this time. So let's dive right in. Now, Douglas Hofstadter won the prize for his work in electron scattering. We'll get to that in a second, but he also did something else that's is still vitally important in labs today. He developed and patented something called a thallium-activated sodium iodide gamma ray detector. Big fancy way of saying it's a method of detecting and measuring gamma rays to some insanely accurate level. And interestingly, yes, he did that work in the 50s, but it's still in use in labs today. It is used widely in labs today as sort of the way you measure that and you measure it correctly. It's just an amazing instrument. And to do that, he had to understand all kinds of things about the nucleus of different atoms. But that gets us to what he won the prize for, which is his electron scattering project. And when you try to scatter electrons through an atom, what happens is the electron can be transmitted directly through it. That can just happen. It can miss completely and move on. It can be elastically scattered and can kind of come back out the other side. It can kind of curve and go off some direction, or it can be inelastically scattered. And what that happens is you kind of just, hit an electron directly on, scatter it out. But along with that, occasionally comes an X-ray that's very characteristic to a specific atom. So if you get an X-ray out of it, you're not going to get a different X-ray out of two different thorium atoms. You're going to get the same X-ray. You're not going to get the same X-ray out of, something that is a noble gas and something that is a metallic. They're going to be completely different. So you can go through the periodic table and now you just look them up and say which X-ray corresponds to which atom. So you can use that to figure out what's in your material. So what that led to is a whole bunch of things, including ways of doing material analysis. Now, that also leads to other things, like it helped us with a lot of fundamental physics and understanding inside the nucleus, and that led to the discovery of quarks. Quarks are inside protons and neutrons. So we thought, for a long time, people thought the atom was the smallest thing. Then we said, nope, here's all this stuff inside the atom, protons, neutrons, electrons, all these other things flying out. And now we've even gone one step further, and everybody said, well, great, the protons, neutrons, electrons are the smallest. Nope, quarks are, you take three quarks to make up a neutron, three quarks to make up a proton. A little bit different ones, but they're there. He helped us with nuclear structure analysis, surface science, material characterization, and these techniques are highly, highly, highly useful if you want to build a thing called an electron microscope. So these sorts of things have changed the way we do science at a fundamental level. And hats off to Douglas Hofstadter. And I really do hope there's truth to the rumor that Leonard was named after him, because that would be really cool. Now, let's dig into the other part of this prize. So Rudolf Mossbauer won his part of the prize for work in what became known as the Mossbauer effect, which is used in, coincidentally, Mossbauer spectroscopy, which really deals with two core concepts. One is recoil-free emission and absorption. That's where a nucleus emits or absorbs a gamma ray, and the nucleus will recoil due to this little thing called conservation of momentum. Very important thing in physics. And the recoil event causes a corresponding and proportional shift in the energy of the gamma ray. And you can that can actually go on to prevent a resonance. So if the in the resonance condition, in order for that to actually work, for resonance to occur, the energy of the emitted gamma ray has to match the energy difference between the nuclear energy levels of that absorbing nucleus, which is a really funny way of saying, hey, if we don't conserve energy, you're not going to emit the right you're not going to emit the right gamma ray. So once energy goes in, it's going to come out in some form. And if you can measure it as it comes out in the gamma spectrum, you can work it backwards and see what's going on inside a nuclear recoil. Now, picture I have of a gamma ray is just for fun. That's not a real lab. Full confession, that's an AI image, but I thought it was cool because it's really hard to image a gamma ray because you can't really see them. Now, the uses of this effect is so highly precise. I mean, we're talking more decimal points of precision than any other that came before it, such that it was used to verify some really important theories. In fact, it was used very specifically to verify Einstein's work, including that on time dilation due to relative motion, things move faster and they get closer to the speed of light, time should dilate. It's been used to measure that and prove that actually works. Now, we can't go the speed of light, so you have to get something moving very quickly and then measure it very precisely. And those two things can combine to tell you whether or not that theory is correct. And that's what they did. It also does measure gravitational redshift, which is another important part of the theory of relativity. So while you may not have heard of Mossbauer, he did help build a technique that allowed us to verify some things that were still kind of in question. So he was very important to the fundamental physics community. And one of the things I came to realize not that long ago, actually, was if you look back about 150 years, technology was much different for humankind. And if you look at the advancement of fundamental science throughout the late 1800s through about 1940, engineers are still catching up on using all that new fundamental science that came about inside that time window. And there's nothing wrong with the engineers, but we made so many advances in such a short period of time that it just sort of like new stuff kept flying out. And these guys developed techniques that allowed even more fundamental science to go on. That'll be the subject of future Nobel Prizes. So keep in mind that now we're getting into the modern technology. And while some of the older prizes, you're like, hey, look, 1905, that led to solar cells, that led to CCD cameras, that led to all that cool stuff. There was Einstein's prize. He did his work in 1905 for the 1921 prize on photoelectric effect. The work we see here is leading to technology we're either starting to realize or will realize soon. So when you start to see some of these things, remember, you may be like, well, what's that good for? Same thing was said about all the work done in the late 1800s, early 1900s that we now really take for sort of granted as part of our everyday effect. Like, the transistor was one of these prizes. So I hope you stay tuned. I hope you click that little like button and subscribe, and we'll see you on the next prize. But we're getting into some really, really cutting edge, newer stuff that I think is going to open up a whole new world for you. So I do hope you enjoyed these videos, and we'll keep doing them. Have a great day.